This is part 2 in a series of videos about stardust. In this video, we're going to talk about the evolution of low-mass stars and their relationship to stardust. So let's start with just talking about how stars die. At the end of a star's life, it's going to run out of fuel. Essentially, stars shine by using fuel in nuclear explosions, and eventually that fuel runs out and the star is going to die. They go through various different stages, but what they end up as depends on their starting mass. For high mass stars, they end in a huge explosion that's known as a supernova. And here we can see the remnant left over from an ancient supernova. Here's another one. This is probably the most famous one, the Crab Nebula. But even low mass stars that do not explode, they die in a much less dramatic way. They still throw material out into space, and they still leave behind fairly attractive corpses. This is a planetary nebula that has a number. This one is a famous one known as the Helix. And then this one is not quite as old. It's called the Egg Nebula. Now, to understand stars and stellar evolution, I have to introduce the idea of the Hertz-Sprung-Russell diagram. All this is a graph where the x-axis, the horizontal axis, is the star's surface temperature, and the y-axis, the vertical axis, is the brightness. Here you can see that is called luminosity. This is luminosities in terms of solar luminosity. So this is the luminosity of the sun here. This is 100 times that, 10,000 times and a million times, and going down to 100th and a 10,000th. Here we have a term called absolute magnitude. That's an astronomy term I'm not going to get into. And here we have spectral type. This is basically how we categorize stars and work out what their temperature is by looking at the spectrum of the star. And so we have another way of denoting the temperature. But for now, the important thing is we have temperature on the x-axis, but it's increasing to the left because we like to do things backwards. And here we have brightness or luminosity. The other thing you'll notice is that this is a log scale. It's not linear. So it's going up by 100, another 100, another 100 times. And here it's not a nice linear scale. It's getting bigger with each step. So this is the Hertz-Sprung-Russell diagram. And if we plot all the stars in the sky, you won't find that there's just random distribution all over. Actually, most stars end up on this diagonal-ish region across the middle of the diagram. You'll also have some stars up here in the reddish area above this line here. You also have some stars up here and some down here. So this main area here is called the main sequence. It is where most stars are. 90% of stars are going to be on this range here. In fact, there's more at this bottom end than there are at the top end. We can talk about that in a different video. And then we have less stars here and even less stars up here. And then there's a few down here. Now, one of the things that we want to think about is, what is it that this is telling us? We're plotting temperature and brightness, but we can also relate this to the size of the stars. So what you think about, if you've got something that is a certain temperature, it's going to glow with a certain brightness. If it is bigger, it's going to be brighter for the same temperature. And so you've got a relationship that puts together the temperature of something, its absolute brightness, the brightness that it is overall, and the size of the thing. So here, if I've got something that is cool, so here we have about 3000 Kelvin, and also quite bright, it must be quite big. And this must be even bigger because it's cool, but even brighter. Similarly, I've got down here something that is quite hot, 25,000 Kelvin, but very low in brightness, less than 100th of the brightness of the sun. So it must be very small. And so we can plot the HR diagram in terms of sizes. So what you can see here is we still have that main sequence. The sun is right here, but then we can put on what that means in radii. So we can see, and this is in terms of the radius of the sun, we can see that the main sequence is close to being the same size as the sun. The hotter stars are a little bit bigger, but only up to about 10 times the size. The cooler stars are a little bit smaller, down to about 1/10 of the size. But they're all within that range, close to the size of the sun. But as we go up into this region up here, now we can see we've got stars that are 10 to 100 times the size of the sun. Those are the giants. And up here, they're 100 to 1,000 times the size of the sun. Those are the supergiants. But down here, to explain the temperature and brightness, they have to be much smaller they're 1/100th of the size of the sun. In fact, they're more like the size of the Earth. And so this HR diagram allows us to understand not only their temperature and brightness, but what that means for their size. Now, the other thing that we can do with the HR diagram, and this is another version of that, is to plot the path on the HR diagram that a star will take over its life. So here again, we've got temperature increasing to the left on the x-axis, and we've got brightness with one solar luminosity being here on the y-axis. And here we can see this would be the main sequence. The sun would be right about here. When the sun dies, and stars like it, it will become bigger. It's getting brighter, but lower in temperature, so it will get bigger. It will then briefly get smaller again, and then it'll get bigger again. And then when we get here, we can see it's staying the same brightness, but it's getting hotter. So it must actually be getting smaller in order for it to get hotter, but not get brighter. We've got something that is shrinking and getting hotter. And then from here, we've got something that is basically staying the same size, but is getting cooler over time. And so this is the evolutionary path of a star like the sun. Okay, so for a sun-like star, basically what we get is on the main sequence, it is burning hydrogen. It is fusing hydrogen to make helium. That is the nuclear reaction that is causing it to shine. When it runs out of hydrogen on the core will actually shrink. But as it shrinks and pulls in hydrogen that wasn't yet used up around it down, that will now start fusing. It will heat up due to the conversion of potential energy to kinetic energy, and it will start burning hydrogen in a shell. So we can see this here. We've got a core in the middle. That's now made of helium because we've used up all the hydrogen, but we've got helium around it, and that is doing fusion. Okay, but that is causing what's outside of it, the rest of the star, to expand. And so what we get is the star becomes bigger. So even though the core is getting smaller, the star gets bigger. Eventually, the core that is collapsing because it's no longer making energy, and so gravity is winning over pressure, the core will get hot enough that helium burning can switch on. And once helium burning switches on, that's the end of this phase, and it will reorganize itself. So we can understand the structure of a star in terms of looking at a cross-section like this, but we can also look at it from the point of view of what does it do on the Hertz-Russell diagram. Like I said, this shell is heating the outer envelope and causing it to expand, and so we have a red giant. As I said, what you're going to get is that the helium in the core is going to start sticking together and fusing to make carbon, but eventually you're going to run out of carbon. And so you go through a similar process again, where the core is made of carbon. You've got some helium that was previously made in a shell around it, and that can be fusing. And you've got some hydrogen in a shell around that, and that can be fusing. They may not be on all the time. They may be fusing and then switch off for a bit, and this one may switch on, and so on. We'll come back to that in a future video. But this will cause this outer envelope to expand again. So instead of just having hydrogen burning causing the outer envelope to expand, we've got helium and hydrogen burning. And so what we get is something that it switched on helium burning, it used up all of its helium, and now it's going to become a red giant again because this hydrogen or helium burning shell is heating the outer layers and causing them to expand. And we call this the asymptotic giant branch, or AGB. And this is where stars produce a lot of material and throw it out into space. So just to see these next to each other, you've got something that was helium in the core and had hydrogen burning in a shell around it. And now you've got carbon in the core and you've got helium and hydrogen in shells around it. So they are both red giant phases. This is one that's called the red giant phase. It's the red giant branch on the Hertz-Russell diagram, whereas this is the asymptotic giant branch. When we think about these low mass stars, basically what happens is you make this carbon core, but it never gets hot enough to fuse the carbon. So it just gets stuck at carbon. We're still getting the helium fusion that we talked about. And that helium fusion, along with just the general structure of the star, means that you've got some instabilities, and the star pulses in a number of different ways. Here you can see it's pulsating on a certain time scale, but it's also got material that's being pulled up from deep down inside. So material that's being made inside the star is being pulled up to the surface. And we'll be discussing that in our next video. But the pulsation means that material gets ejected. You've got this pulse that causes the surface to push outwards, and that allows material to disappear out into space. And some of that material will be newly formed stuff from deep down inside that's been pulled up to the surface by these convection currents that we can see here. Now let's just talk about the pulsation. There are two different flavors of pulsation. I'm going to talk about the one that is happening because of the structure of the star in the mantle of the star, not the helium burning area. So you can imagine something where within the star, it's basically completely ionized deep down inside. It's really hot. And as you're coming up to the surface, you've got more and more of the gases is not as ionized. So instead of having heliums that have no electrons attached, now you've got some heliums that have electrons attached. That's going to change the opacity, and it allows some light to go through. And if you've got both of the electrons attached to the helium, well, now you've got something that changes the opacity again. How much light is reflected, absorbed, or allowed to go straight through depends on what the particles are made of. And so here what you can see is whether radiation can get out depends on how opaque this area is. If the radiation can't get out and it's being absorbed in here, it's going to cause this area to expand. But once it expands, it's going to be lower density. And so you're going to have spaces between the atoms, and it's going to cool in that expansion. The cooling from the expansion means that the ions will actually recombine. So instead of having, say, a helium 2+, you might just have a helium plus, or instead of having a helium plus, you've got a neutral helium. And that makes it even more transparent. And so radiation now just flows straight out and the area cools. And so now gravity begins to win and it will shrink back down again. But as it shrinks back down, it's heating up again. And so electrons get knocked off again. And so the helium goes to helium plus, and helium plus goes to helium 2+, and that changes the opacity and it becomes more absorbing. And now it's going to get hot again and it's going to expand. But in doing so, it's also going to cool and allow recombination. And so you're back to square one. And so you get something that's never able to reach equilibrium. Every time it expands, it cools and it changes the state of the ions. And so it changes the opacity. And when it shrinks, it loses electrons and changes the opacity again. And so it can never get to an equilibrium position. And so that's why we get pulsation in these types of stars. It has to do with the level of the density and the ions that are in the mantle of the star. Okay, so I want to consider what's going on with the stars that we're looking at. And what this table is showing you is a star like the sun, and it will be a main sequence star for about 10 billion years. But the important thing here is the sizes. So at the peak of the red giant branch, just before the helium switch is on, it's going to be about 100 times its current size. And that's about 0.5 AU, or halfway between the Earth and the sun. So the sun's surface has moved out a long way. But in that second red giant branch, when you've got a carbon core and you've got helium burning or hydrogen burning going on around the core, now it's 500 times its current size. And at that size, it will swallow not just Earth, but also Mars. In fact, the surface will be out in the asteroid belt. And so this thing is huge. Why is that important? Well, remember that we have pulsation. And so as the star pulsates, it's pushing material out at the surface as it moves outwards. But now it's got the same or even less mass than it had on the main sequence. And so its gravity is very low at the surface. Remember that gravity goes down as 1/r². So even though you've got the same amount of mass, your surface is now much, much further away, 500 times further away. So the surface gravity is low. So it's much more easy for the atoms to achieve escape velocity and just disappear off into space. So here's that HR diagram that we were looking at before for the sun. The sun starts here on the main sequence, becomes a red giant star, and then an asymptotic giant branch star. And during the asymptotic giant branch, those pulsations are giving rise to material drifting off into space. And what we're looking at here, this is IRC 10216, which is also known as CW Leo. It's in the constellation Leo. And we're actually seeing the reflection from dust. And this dust is what forms as a result of that material being thrown out through the pulsations. Once the star reaches this point, there's basically not enough material left in the star itself. So much has been thrown out in space that the density is really low and the pressure is too low and gravity wins. And so the outer layers just start to collapse in. But as they collapse, they're converting potential energy to kinetic energy. And so it starts to heat up. And so what we've got here is you're actually seeing, again, those dust shells, just like we see here. We've got dust that was thrown out during the AGB phase, but light is being reflected from them towards us. But once we get to about this temperature, around 30,000 Kelvin, now you've got enough high energy photons that you'll start to ionize the gas that is in and amongst the dust, and you'll get a planetary nebula. It's going to keep heating up until it cannot collapse down any further. And at that point, it may be as hot as 200,000 Kelvin, and it's still ionizing this material that was previously lost during the AGB phase. The central star will then just cool. It has no longer any fuel. And so the central star is a white dwarf at 200,000 Kelvin, and it will just cool until it cools to the temperature of the universe. The shell that is around it of gas and dust, that will just drift off into space. Just to give you an idea of how much material is being lost, typical mass loss rates, they actually will change over the course of the star's evolution, but they're of the order of 10 to the minus 6, a millionth of a solar mass per year. Now, that might not sound like a lot, but the solar wind is at highest 10 to the minus 15 solar masses per year, and it's more like 10 to the minus 20. So 10 to the minus 6 solar masses per year is a lot of material being thrown off every year. At the same time, it's not moving very fast. The solar wind moves at 200 to 1,000 kilometers per second. So what you've got is material that is being thrown off the surface of the star at a high rate, but not very fast. And so the density of atoms close to the star is very high. And so that's how you can form dust, which is what we're seeing reflecting light here and here, because you have enough atoms in contact with each other to have dust condense as the gas gets cool enough as it flows away from the star. And that's all we're going to talk about for this video. In our next video, we will look at more detail how AGB stars work and what we can learn about the dust that goes on to enrich the rest of space.